This is Algebra 2, Lesson 2-6, Families of Functions. A parent function is the simplest form in a set of functions that form a family. For example, y equals x is the simplest form of a linear family. A transformation is a change from the parent function. There are 4 types of transformations: a dilation, a reflection, a rotation, and a translation. A translation is shifting a parent function horizontally, vertically, or both. It does not change the shape or the orientation. In other words, it stays in the same shape and it also stays in the same position. It doesn't rotate or flip. A reflection flips the graph of a function across a line, such as the x or y axis. And a vertical stretch multiplies all y values of a function by the same factor greater than 1. And so if you want to make your thing stretch, you're going to multiply it by a number greater than 1. If you want to do a vertical compression, you're going to reduce all your y values of the function by the same factor between 0 and 1. In other words, you're going to multiply it by a fraction or a decimal. Now, it's helpful to understand basic parent functions and their graphs. There are many parent functions, but today we will only be looking at 2, linear functions and quadratic functions. A linear function is y equals x, or f of x equals x. It goes through the origin, and it's just a line that goes through the origin. It has a slope of 1, up 1 to the right 1, up 1 to the right 1. The quadratic function, the parent quadratic function, is y equals x squared, or f of x equals x squared. If you were to make a little table of values for your f of x equals x squared, if I have -3 squared is 9. -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. Hence, you see how they got this graph that looks like this U-shape that they have right here that I will highlight. This is the U-shaped graph, and it's found by doing these points over here. Okay? A quadratic function is always a U-shaped graph. Now, there's easy ways and hard ways to transform a parent function. We did some of these in Algebra 1, and hopefully you remember some of them. If you are going to be working with a positive constant k in the parent function, okay, so you have the parent function f of x. If you have f of x equals plus or minus k, it's a vertical translation. Okay? For example, in this first one right here, f of x plus k, okay, shifts the graph up k units. So if I had f of x equals x plus 2, my graph would shift up 2 units. It would still have the same exact shape, same exact size. It would just move all of the points up 2 units. If the k was negative, it's going to shift it down that many units. Now, if everything is in the parentheses, if you have f of parentheses x plus h, okay, so if I have f of x equals parentheses x plus 2, and everything is in the parentheses, this will go left 2 units. And it seems opposite of what you would think it would be, but since everything is in the parentheses, if I was going to solve x plus 2, if I have x plus 2 equals 0, if I'm going to solve this, I would subtract 2. So therefore, x equals -2, which is why it would go left 2 units. Okay, so it's opposite of what your brain thinks it should do, but it actually is correct. And of course, if it's x minus h, it's going to shift to the right 2 units. Okay, these are important things to understand because they help you understand how to deal with moving graphs, translating graphs, without having to redo all the x and y tables. Okay, let's take a look at something. We're going to graph the parent function in 2 vertical translations on the same axis. Y equals x squared. Remember, we did one just like this just a minute ago when I had the y equals x squared here. We'll just put this down here. I'll do -3, so this would be -3 squared is 9, -2 is 4, -1 is 1, 0 is 1, 0 is 0, excuse me. 1, 1, 2 is 4, and 3 is 9. Okay. We obviously can't graph all of those, so I'm just going to basically graph from -2 on. So if I do -2, -2, 1, 2, 3, 4, here's my first point, -1, 1, 0, 0. Remember, these are symmetrical. So this point here is 2 units if this point right here is 2 units from the y-axis, its parent point, its symmetrical point should be 2 units from the right of the axis. So it's really easy to graph a y equals graph because you just have to find one side of it and then just make it symmetrical. So there's the graph of y equals x squared. That's the parent function. This would be our parent function. Now, we do not need to make tables for the translations. We can simply look at them. If I look at y equals x squared minus 1, this next one here, x squared minus 1, there's nothing in parentheses, which means it shifts the entire graph down 1 unit. So I just take each point and move it down 1 unit. So the origin goes down here, and these points that were at -1, 1, that goes to 0, -1, or -1, 0. And then 1, 1 goes to 1, 0. These units would shift down 1, so this one goes here, this one goes here, and this is my new graph right here. And then it's another curve. And there you have it. It's not very symmetrical. I did a very good job making it very symmetrical. Right. And the last one, x squared plus 4, we're going to use the green graph, and we're going to shift them all up 4 units. So here, this would go up 4 units. My point of the origin would go up 4 units, 1, 2, 3, 4. That goes here. This point will go up 4. The 1, 1 will go up to 1, 5. So that's here. It has a counterpart over here. And the other ones are off the graph, so I'm just going to have to interpret this a little bit. And there we have the graph of y equals x squared plus 4. It's very easy to make vertical translations and horizontal translations once you know the parent function. Okay? It's very simple to do. Let's do some horizontal translations. Okay? Notice this is still the parent function of y equals x squared because we have a square here. And we have a square right here. So this is still a parent function of y equals x squared. So the y equals x squared, if you remember, looks like this. Here's the y equals x squared graph. That would be this one. I'm going to circle it so we know which one is which color. Now, if we're going to do the y equals x plus 2, plus 2 means we're doing a shift to the left 2 units. So all we have to do now is move all our points 2 units to the left. So my origin point here moves 2 units to the left, so it's now at 0, -2. The point to the left of the origin moves 2 units to the left, so it's here. This one moves to this point. This point here moves 2 units to the left. 1, 2 goes here. This one goes 1, 2 here. So my new points then for this graph look like this. Same size, same shape, just moved. And if you color code, you don't have to label them on your graphs. If you don't color code them, you better label them on your graphs. I color coded mine here by doing this, so therefore I know which one is which. Now, let's summarize some of the transformations. We didn't talk about all of these, but we will work with all of these in just a second. So, this is something that's probably very important for you to write down. Whenever you see something in a box, it's probably very important for you to write down. The transformations of the parent function of f of x. A vertical transformation, if you have k being greater than 0, you're going to go up k units. Okay? If k is less than 0, okay, oops, this should say less than 0 right there. K is less than 0, you're going to go down k units. Okay? If you have a horizontal translation, okay, you're going to move to the right and to the left. And this is correct because we subtracted it. Since we're subtracting it, k is still, as we're focusing on that point. So if you have your translation, this is going to move you left, this is going to move you right. The couple we didn't talk about is a vertical stretch and a compression and the reflections. A vertical stretch, if a is greater than 1, it's going to stretch it. If a is between 0 and 1, it's going to shrink it. And I'll show you what that looks like on a graph in just a moment. And in a reflection, if you're going to reflect over the x-axis, you're just going to take a negative and run it through the function. If you're going to reflect over the y-axis, you're going to replace x with negative x. Very simple to do, really easy types of transformations. So let's take a look at some of these. And since this is written in green, I will change my color. Let g of x be the reflection of f of x equals 2x minus 7 in the x-axis. What is the function rule for g of x? Okay, so since it is a vertical, okay, so actually it's a reflection in the x-axis. Okay. So it's right there, reflection in the x-axis. Remember, the x-axis is you're going to do y equals negative f of x. You're going to do that particular function. So my g of x function then, g of x, is going to equal the negative of 2x minus 7. So all I'm doing is I take my f of x, which is this, and I put a negative in front of it. So that's what I did down here. Now I run that negative through, so g of x then will equal negative 2x plus 7. And that's the reflection of f of x equals 2x minus 7 in the x-axis. That's going to reflect it across the x-axis. So let's let h of x be the reflection of f of x equals 2x minus 7 in the y-axis. Now we're going to do the y-axis. We're going to show you the difference between reflecting something across the x-axis and reflecting something across the y-axis. A y-axis reflection is so a reflection across the y-axis is y equals f of negative x, which means we're going to replace x with negative x every time we see it. So in my function, h of x then would equal 2 times negative x minus 7. So h of x then equals negative 2x minus 7. You'll notice the subtle differences between these two equations. In the equation over the x-axis, the negative 7 becomes positive 7, and the 2 becomes a negative 2. In the y-axis, the negative 7 stays a negative 7, and 2x goes to a negative 2x. All right, let's stretch or compress a function. And below here, we have on this lovely graph, we have the function of f of x. It's shown below. What is the graph of h of x if h of x equals 0.5 f of x? Okay, so in other words, we're going to take everything and multiply it by a half. Okay? Since this is a vertical compression, okay, it's all of the vertical points are going to get shrunk by a half. All of the horizontal coordinates are going to stay the same. So I'll make a little table just to make it easier for you for just a second. But it's just as easy to do without a table. Okay, so we're going to have x here, f of x here, and then we're going to have 0.5 f of x. Okay, so I'm just going to put down my x coordinates. So at this point right here, my x coordinate is 0. Okay, my f of x coordinate is 3, because that's the x and y. Remember, this is the same thing as saying x and y. My 0.5 f of x means I'm going to multiply 3 times 0.5, which makes it 1.5. My second point here will be this one. My x value is 1, my f of x value is 0, and 1 times 0.5 gives me 0.5. My third point, right here, my x value is 4, my y value is 3, so my 0.5 f of x is going to be 4 times 0.5, which is going to make it 2. And last but not least, this point right here, my x value is 5. Oh, it's 7, excuse me. I can read. It's 7. My y value is 2. Okay. So if I'm going to do my point, oops, I did the wrong value here. I just realized that right here I did the wrong value. I did the wrong value of this one too. Silly me. Let's go back. We're supposed to be doing the y values, not the x values. Okay. So this is going to be 1 times 0.5. So 0 times 0.5, I did it again. Boy, I'm not going with that. So it's going to be 0 times 0.5, which makes this be 0. I can do this a lot better without the table. This one's going to be 3 times 0.5, which is going to be 1.5. And right here, this last one right here, is going to be 2 times 0.5, so it's going to be 1. Right? The easiest way for me to do these is not do them with a table, but to just look at the graph itself and say, okay, this is at 3, what's half of that? Well, that's 1.5. Well, that would make that point here. Half of 0 is still 0. Half of 3 is 1.5 again. And half of 2 is 1. So then I would redraw my graph. And here's the graph of h of x equaling 0.5 f of x. It's just as easy, just take the y values, just take your y values right here, and multiply them by 0.5 to get your new y values. And if we use a whole number, it would just make it bigger and it would stretch it, make it taller. Now you can combine transformations. You can have horizontal and vertical and reflections and transformations all at the same time. Let's take a look at this one. The function f of x equals 8x. The graph of g of x is f of x vertically compressed by a factor of 0.5 and reflected in the x-axis. So what's our new function word? Okay. So easiest thing to do, right? If it's going to be vertically compressed, I know I'm going to have to multiply this by the 8x. Right? So I'm going to do that first. So my new rule for g of x is going to be 0.5 times 8x. That gives it, g of x is going to be 4x so far. That took care of my compression. Now I need to take care of my reflection. Okay. And my reflection in the x-axis, if you remember the reflection in the x-axis just takes your f of x and makes it for the x-axis, y equals negative f of x. Okay, so I'm just going to change this now to g of x will equal negative 4x. There I have done both transformations. I have compressed it and I've reflected it at the same time. Take a look at the second one. But transformations change the graph of f of x to the graph of g of x. We have f of x equals x cubed and g of x equals x plus 4 quantity cubed minus 1. So now they gave us the equation, and we have to say what happened to it. Right? This is my parent function right here. So I need to see what happened. Okay? This right here tells me it went down 1 unit. This right here, that right there tells me it went left 4 units. So, what did it do? What transformations? So this is a horizontal translation. Units left. And a vertical translation. One unit down.